Section 12.7, tangent planes and linear approximations with differentials, may I add. It's a quite a long title, so I just cut it off. We talked about the planes earlier. We know what the equation for the plane is. We also know from Calculus 1 that there are tangent lines. So now when you have a surface, you will have a tangent plane. We are going to figure out how to compute, find tangent planes, compute, and see what they're good for in this particular section. So first we are going to go through quickly through a procedure to find the tangent line from Calc 1. So Calc 1, right, with case. Find tangent line at, I don't know, x equals to 3 for f of x equals to a function over here, x squared plus 1, whatever. So the way for us to find the tangent plane, you either remembered the linearization or you remembered the procedure for the tangent plane. They all are equivalent, they're all the same. So what we do is we find the derivative first, which in this case is 2x. Then we compute that derivative at point 3, and we get 6. And that is the slope. So slope is 6. Then we compute the f of 3, which is 10. And now look what we have. We have m is equal to 6, and we have a point 310. So now we can use y equal mx plus b to write 10 is equal to 6 times 3 plus b. So that's 18, negative 8, so b is negative 8. So the tangent line at x equals to 3 is given as y equals 6x minus 8. And that would be the answer. Now, what was the tangent line good for? Well, if I am to graph my, parabola like this, and I pick this tangent line shows the rate of change at that point. It is also the direction in which the object wants to move. If the function that we have is the path for a particle or something, then the tangent line is the direction in which it's the direction of the velocity. So now we are moving into Calc 3 to talk about tangent planes. First, we review the equation for the plane, and we had those two forms. If you remember it, it was the, anyone? No? Just crickets on the other. Minus x0. Excellent. And then there was the shorter version, which was ax plus by plus cz equals to some kind of d, which was the combination of ax0, b, and so on. So we have this. Now, if you compare equation of the plane and you compare that to the equation for the tangent line that we had before, so tangent line, if you remember the linearization way to write it, was f of a plus f prime of a times x minus a. Do you see how you have this term x minus a, which reminds you of x minus x0, y minus y0? And you see that you have derivative in front? So that's exactly where the tangent plane comes in. You can have the partial derivative x minus x minus x0 plus fy y minus y0 plus fz z minus z0 equal to 0. To write this in a vector form, you have your del f computed at AB, and then, well, let's just call it del F because we can keep it for 2 or 3 dimensions. So we have del F dotted with the vector R minus R0 is equal to 0. Both of these are equations for tangent plane. One is a vector equation. So every surface will have the tangent plane. Now, depending whether we are having a 2D or 3D case, you'll be computing at AB or at ABC for all of these calculations. So a quick example. I don't know, 18, whatever. Z equals 2 plus 2x squared plus 1/2 y squared. And we want to find that point -1/2, 1, and 3. So clearly, the point -1/2, 1, and 3 is the only point that the plane and the surface would share. One more time, I'm going to paint the picture for you. This is a three-dimensional object, and this is the tangent plane. In mathematics, we use the word kisses if they touch at exactly one point. So the tangent plane kisses the surface at exactly the point, and that's going to be our -1/2, 1, and 3. So that would be the tangent plane in this case. And then as the object, has different, it's important that the tangent plane is perpendicular to the surface of the object. The surface of the object has the curvature that will have a radius somewhere, and that radius is what we are looking for. So that's what's happening here. Tangent plane, right? Ever wondered why the graduation gear is what it is? It's just a tangent plane. So when you graduate, you all get another tangent plane. And you get that. That's what it is. While you are sitting at the ceremony, you can be discussing that with whoever's sitting next to you and then work out these equations. The time would go much faster. All right. We are going to take a look at this. Exactly. So we are going to first find the implicit form of the problem, and that would be that this f of x, y, and z is equal to 2x squared plus 1/2 y squared minus z, and then plus 2. I'll put plus 2 at the end. Equal to 0. And now we are going to find the partial derivatives, which will create our gradient vector. So gradient vector of f is going to be fx, fy, and fz. So partial derivative in respect to x is 4x. Partial derivative in respect to this is just y. And then -1. That's the gradient vector. Now this serves the purpose of the normal vector for planes. And this is, well, remind me to talk about the normal vector from the unit normal vector and this, because there was a question, there were two questions actually, confusing the normal vector for the planes and the normal vector, the principal unit normal vector. So we'll have to talk about that and distinguish between the two. So now what do I have? To find the normal vector for the tangent plane, I have to take the gradient vector and compute that at -1/2, 1, and 3. So 4x times -1/2 is -2, y would be 1, and then we still have -1 at the end. Nothing to plug in, nothing to compute, just -1. Now guys, this is your normal vector. This is your ABC from the good old section we did. So what is the tangent plane, TP? Tangent plane is going to be -2, x minus, what's the first coordinate? Half, so plus a half. Plus 1, y minus 1, minus z minus 3 is equal to 0. So let's color code a little bit. This, and this is your vector n, which you calculated through the normal vector. And now in blue, this, and this is your point P that is given to you, point at which you are looking the tangent plane, right? So now we can clean this up a little bit. We have -2x plus y minus z is equal to, is going to be -1, -2, so -1, right? -1 minus 1 is -2, and then plus 3 is +1 and goes to the other side, -1. So this is the tangent plane. We utilized the gradient. So let's recap problem 18. We start with the function z equals 2 plus 2x squared plus 1/2 y squared. And we have the point P at which we want to center our plane, tangent plane. Or we want to find the tangent plane at that point. So now, we first create the implicit form for the function. We move z to the other side. We create this capital F function, which is implicit. And then you solve the partial derivative. You find partial derivatives, which gives you the vector of partial derivatives, which is the gradient. When you compute that gradient at the point provided to you, you are getting the vector n, which is the normal vector for the plane. Plug in the normal vector, plug in the point, and you have equation of the plane, and simply simplify, and problem solved. So, as long as you remember, we'll do another example. Tangent plane. I mean, that's 100% question on the test and the final. I mean, there's no way you should have a test or a final in Calc 1 without tangent line and in Calc 3 without tangent plane. It's one of the key concepts of the course. Derivatives measure change, and tangent plane is there to measure the change for the 3D objects. So that's the key component. This piece is the key component for the differentiation. Yes? Let's take a look at one more. Anything 19 through 24? 21. You're constantly picking those that you can do at home and check. Z equals, but it's a quality one, so it's good. X squared e to the x minus y, sponsored by Mary. And the point at which we are going to take a look is 2, 2, 4. All right, so you have about 17 seconds. Go.
You don't put the notation there, you just put the then. Like one, two numbers are wrong. That won't be wrong. It's like the same like when car brakes, right? You just car brakes, you just leave the car, just abandon and just leave. That's how we deal with problems. We don't go back checking, figuring out what we're gonna fix it or something. No, we just leave. Huh? Yeah. Next one. Never mind, you still have 16,000 on and figure for sure. Everything is broken.
All right, let's take a look at this problem together. Everything okay? I didn't check the roster before we walked in. I was like, there goes the curve. X squared e x minus y minus z equals to 0. So that would be our first thing. Then we have del f in respect to x, y, z. So partial derivative in respect to x, well, that's the product rule, so copy the first one times the derivative of the second plus copy the second and then derivative of the first. Then in respect to y, we copy everything, so it's minus x squared e to the x minus y, and then derivative in respect to z is negative 1. Do we agree on the derivative, everyone? Thank you. Now we are going to compute that one at our point. So 2 minus 2 is 0, so that's 1, so that's 4. Plus, so that first one is 8. Compute the second one, one's negative 4. And then negative 1. Nothing to compute that, just copy. Now that is our vector n. And all we need to do now is to put the tangent plane together. So 8 x minus 2 minus 4 y minus 2 minus 1 z plus 4 equals to 0. So we have 8x minus 4y minus z is equal to, and then we have negative 16, negative 8, z minus 4. So this is negative 4 on the other side? No, positive 4. There we go. Perfect. Linear approximations. So now, all we need to do is to rearrange this into a form where we can use it as a linear approximation. We already have the tangent plane. So now the linear approximation of xy, because remember it's a two-dimensional input, x and y are independent, z is the dependent variable. We use the tangent plane without the z term. So it's fx x minus a plus fy y minus b plus f of ab. Now you might be a little bit wary of what is. Oh, I forgot to put this is computed at a. Okay, if I put it this way, it's going to be weird. So these need to be computed at AB. So if you move f of AB, the last term, to the left, you will have L minus F. That's like saying Z minus the point. And then you have all the derivatives. So this is the linearization formula. Now the story of this, guys, is the same like the story in Calculus 1. Unfortunately, or fortunately, we have technology today, so we're not going to compute this ever. This is more the concept to honor the ancestors than something that we really need to know today. You need to know the concept of this, but then calculators, computers, Mathematica is just going to put all of these computations for you, so we really don't use this at all, ever, today. So what is the whole idea? I'll explain through Calc 1, and then it's easy to understand Calc 3. So if you have something that you want to compute, let's say you want to compute ln of 3. And you ask yourself, how much is ln of 3? Now, we always have to paint the scenery, right? You're at the desert island, you have no calculator, you have no phone, all the batteries are there. Maybe you have them, but the batteries are done. Wilson is gone. You have nothing to do, right? You want to know, yes, you want to rediscover the entire chart of all the ln's and everything. How do you compute the value of ln3? Well, you are going to compute a linear line that is tangent to the point very close to ln3, and then you are going to compute 3 in that tangent line, which is just a linear, stick in the sand and you're good to go, instead of computing in ln3. So if this is 1, and this is 2, and this is 3, you will find the tangent line, right? Sorry. You will find the tangent line at the point that it's close to 3. So that will be here, and that's E. So you find the tangent line at E, and the y value for the tangent line is going to be almost the same as the y value for the original line. See? Almost the same. So this is the tangent line, and this is the function. So we find the tangent line at x equals e, because that's something that is easy, cheap to compute. And then we just compute, once we have the tangent line y equal mx plus b, we will plug this 3 in there, and we would get some number. That number will be very close to this number. The same thing now transfers to calculus 3. You have some crazy shape with crazy functions, with crazy everything, and you don't feel like computing it. You find the tangent plane to the point close to the point you want to compute, and then you plug your x, y, and z that you were supposed to compute in the original function into the plane equation, and you compute there. So same idea, same motivation, same everything like in Calc 1 with tangent lines. Now we do that in Calc 3 with tangent planes. And we call that linear approximation because x, y, and z have no exponents on it. All right, so this is linear mathematics. So let's do an example. Do you want to do 28? Yes or no? Yes, that's the spirit. We do the 28. F of xy is equal to the square root of x squared plus y squared. We're going to find at 3, -4. This is so... No. Wow. Compute this book. Holy nightmare. Come on. There we go. So this is how question should look like, without extra bells and whistles. You should know that you are supposed to find the tangent plane at 3, -4, because that's what the numbers, right? This number here is close to 3, and this number here is close to -4. So that is the knowledge that you did. The book just gave everything, and I didn't read quick enough. So you have the function, and now you can do one of the two things. You can take these two numbers, put them here, use your calculator, right, and compute. But remember, desert island stuff, so you don't have it. So instead, find the tangent plane at 3, -4. When you get the tangent plane, you're going to get some easy numbers there. And then when you plug these decimals, it's something that you can work out with a stick in the sand. Let's go. So find the tangent plane at 3, -4 first. Gradients, all that kind of stuff. Well, you have a function for this, it's computed at 3, -4. Put that together, and then I'll do it.
Nothing makes any more for computation because we have all of the things to compute. This is for us to honor the answer.
What else are you gonna do? Go home cold?
We sit here doing linear approximation. X and Y are those. Three of them. And A and E are three.
Definitely answers.
You got six?
No, I didn't do it. It's so hard to do math in 10 sometimes when you know you're going to mess up. I'm just letting it drop it out. It's so true. I only do math in 10, so I can't do the problem. No, I'm getting I don't want a pencil, so I don't see what they're like tempting me to have like I felt so bad. They should use that as just like for me, have like a rough day. He like erased everything.
How about the
You guys good? Let's go and see that the answer is not 6. So these are our x and y for the end to compute. We have the a and b as 3, -4. So we find the partial derivatives. Fx is equal to 1/2 x squared plus y squared to the -1/2 times the derivative of the inside, which is 2x. Fy is symmetric. And now we do the linearization. So L of xy is equal to the partial derivative computed at, well, half will cancel. Partial derivative computed at 3, -4. So that's 3/5 and the -4/5. X minus 3 plus minus 4/5 y plus 4, and then plus compute the function is just 5. Are we all good on this? So now this is where you compute 306, and I mean, we can simplify this, put the fractions together and all of that, but I don't know if you actually gain anything. So now you would plug in 3.06 here, and you would plug in negative 3.92 on the other one. Get LXY to be 3/5 times, now this is going to be 0.06, so that's 6 over 100, minus 4/5. When we do this, it's 8 over 100, and plus 5. Is this all good? So now let's compute this. Remember, no calculator, no computer, so we have to figure out. So these guys cancel. 6 over 100 to 3 over 50. So it's 9 over 250. Minus, these guys cancel by, again, I want the common denominator, so I'm going to cancel by 2. So 4, so 16 over 250. And then plus, I need 250, so that's going to be times 50. What happened? Yeah. So times 250 is 750 over 250. And the answer is over 250. $750 minus this, it's going to be 734 plus 9, 743. What happened? Why 1250?
250 times 3 is 750 plus 9,500. So
We need 5 times 250, right? Or the 3 times is this. Yeah, it's 1250, right? So the answer over here, so that was 750 plus 500, 1243, right? Anyone got this?
We did the 500 plus 5.
So plus 5 comes from the computing the function. So when I plug in 3 and 4 squared, that's 9 plus 16, 25 squared root of 25 is 5. I will finish more. There's also differentials, but we only have 4 minutes, so I can't go through the word problems in 4 minutes and all this cool stuff that's gonna be there on the test. So we'll finish this lecture on Monday.